A long cylindrical conductor of radius A carries a uniform current I. What is the magnitude of the magnetic field at R less than or equal to A, so inside the radius of the cylinder, and R greater than or equal to A, outside the cylinder? Let's begin with a sketch of our cylinder. We have a cylinder of radius A. This cylinder carries a uniform current. That uniform current I'll illustrate as I. And this current, being uniform, is distributed throughout the volume of the cylinder. So I'm going to represent the current at the end of the cylinder with a bunch of X's, indicating that the current is going down the length of the cylinder. Now we want to find the magnetic field at a point inside the cylinder. So we will say at a distance R away from the center of the cylinder. We know that Ampere's law can help us find the magnetic field that way, because Ampere's law says the line integral of magnetic field on a closed loop is equal to mu naught times the current enclosed by the loop. So to figure out what we should use, let's look at our cylinder from a different perspective. Let's say we're looking at the cylinder from the near end. Looking at the near end, the current is uniform and moving away from us. So these X's represent the current is moving away. Ampere's law says when we take the line integral of the magnetic field on a closed Amperian loop, that is equal to the product of the permeability of free space times the current enclosed by that loop. So let me put an enclosed here to emphasize that it's only the current inside the loop. Now, an Amperian loop, remember, doesn't have to be a physical curve in space. It just has to be a mathematical representation of a curve. So we could choose any curve we want. Now, the best curve to choose would be a curve that matches the symmetry of the magnetic field. So if we were to take the magnetic field due to these current contributions at a distance R from the center of our cylinder, we would see that the right-hand rule would give us a magnetic field line that is centered on the center of the cylinder. And it would say that the orientation is clockwise using the right-hand rule. So let us take that magnetic field line and use it as the basis of our Amperian loop. So our Amperian loop will then be a circle. And that circle matches the symmetry of the magnetic field. This means that the magnetic field must be tangent to the circle at all points around the circle. And let me redraw that. Here is our Amperian loop, and our magnetic field is tangent at all points on the Amperian loop. So our Amperian loop, being a circle, has radius r. We could look at various length differentials of our Amperian loop. So our Amperian loop has tiny segments dl all the way around. We just have to look at the relationship between that tiny element of loop and our magnetic field. And notice that the angle between the magnetic field and our tiny element of loop at all points on the loop is equal to 0. So I'll represent that as the angle between the magnetic field and a segment of the loop being equal to 0. Now that's a useful thing to know because it allows us to rewrite the dot product in Ampere's law as the magnitude of the magnetic field times the cosine of the angle between the magnetic field and our loop element, dl. And we know that that is equal to mu naught I enclosed. Now, since the angle between the magnetic field and our current element is equal to 0, the cosine of 0 is equal to 1, and this means that we have the integral of B dl, the magnetic field, and our segment of loop is equal to mu naught I enclosed. Now our magnetic field is constant everywhere on the loop, so this is just the integral of dl is equal to mu naught I enclosed. And when we integrate dl, we just get L. And L is just going to be the circumference of a circle. So we get that the product of the magnetic field times the circumference of the circle, 2 pi r, so there is our r dependency right there, is equal to mu naught times I enclosed, or the magnitude of the magnetic field is mu naught I enclosed over 2 pi r. Well, this is great. This is a relationship we've seen before for straight wires. But here's the thing. I enclosed. I enclosed is only the current enclosed by our Amperian loop. If we look back at our diagram, notice from this diagram here, only 4 x's are contained within the loop, representing a portion of current, and the rest of the current is outside the loop. So we don't know specifically how much current is enclosed by this Amperian loop. So we know one thing. We know that the current is uniform, which means that the current density is given as current per unit area, and that current per unit area is the current enclosed by our Amperian loop over the area of our Amperian loop. And that current per unit area of our Amperian loop must be equal to the current in our entire wire over the cross-sectional area of our entire wire, because the current density is constant, meaning the current is uniform. Let's take the current density within our Amperian loop, relate it to the current density of our entire wire, and integrate both sides with respect to the area enclosed. When we do that, the left side is just the integral of the current enclosed, and the right side is just the integral of the area that is enclosing the current. So this means that the current that is enclosed by our Amperian loop is equal to the current times the ratio of our area of our Amperian loop over the overall area of our wire. Therefore, I enclosed is equal to I times pi r squared, being the area, the cross-sectional area of our Amperian loop, over pi a squared, being the area of our wire. The pi's cancel, and we have that I enclosed by our Amperian loop is equal to the current in the wire times the ratio of the distance from the center of the wire or the center of the cylinder to our point in the cylinder over the radius of the cylinder squared. We can use this now to come up with the expression for our magnetic field within the cylinder. Because the magnetic field, the magnitude is equal to mu naught I enclosed over 2 pi times the distance from the center of the cylinder. This is just mu naught over 2 pi times the distance from the center of the cylinder to our point times I r squared over a squared. An r in the denominator cancels an r in the numerator. And we now have an expression for the magnetic field at a point inside the cylinder. The magnetic field is equal to mu naught I over 2 pi a squared r. And this is a point for a point inside the cylinder. Notice that this says that when r is equal to 0, the magnetic field is equal to 0. Well, does that make sense? Absolutely, because remember, Ampere's law says that the line integral of the magnetic field is equal to the product of the permeability of free space and the current enclosed by an Amperian loop. So if our current is moving straight away from us, but the radius of our Amperian loop is 0, our loop encloses 0 current. Since our loop encloses 0 current, there is 0 magnetic field. So that makes sense. And notice also something else about this expression. This expression says the magnetic field varies linearly with distance from the center of the cylinder. So if we have a horizontal axis representing distance, and if we have a vertical axis representing the magnetic field, and here we'll represent A for the radius of the cylinder, the magnetic field varies linearly until we get to the cylinder's radius. Now that makes sense too, because as your Amperian loop gets bigger and bigger and bigger, you're enclosing more and more current. So it makes sense that the magnetic field is increasing as you're enclosing more current. Now let's find the magnetic field outside of our cylinder. Now we said that this is a long cylinder. So this long cylinder can be really treated like a long wire. And the current is moving through our long cylinder, and our long cylinder has a radius of A. Well, we could use Ampere's law to find the magnetic field at a point outside of our long cylinder. We'll say the point is right here, and that distance is going to be r. Now, we've already shown what the result of this should be. Since we can treat this long cylinder as a long wire, and since we are looking at the magnetic field outside of this long wire, we already know that the magnetic field should be equal to mu naught I over 2 pi r, where I is the current enclosed by our Amperian loop, And at the distance r away from the center of the cylinder, our Amperian loop will form a circle with a clockwise orientation as given by the right-hand rule. Oh, and I forgot to have my r in the denominator over here. So here is our expression for the magnetic field due to this long cylinder for a point outside of the radius of the cylinder. Well, let's look at what we have now. We have, if we look at the magnetic field at a distance of a, so basically on the surface of the cylinder, this would be equal to mu naught I over 2 pi a. Now let's look at our other formula that we derived previously. Remember, when we are at a point inside the cylinder, the magnetic field was equal to mu naught over 2 pi a squared I r. Now, if r is equal to a, this is mu naught I a over 2 pi a squared. A in the numerator cancels with 1 in the denominator, and we get that the magnetic field at the surface of the cylinder, due to our first derivation, is mu naught I over 2 pi a. Notice that these two results are the same. So at the surface of the cylinder, our expression using Ampere's law inside the cylinder and our expression using Ampere's law outside the cylinder ends up with the same value, which makes sense because the magnetic field needs to be continuous. Now let's look at what a graph of this looks like. So if the horizontal axis represents radius and the vertical axis represents magnetic field, and we have the surface of the cylinder at point A on the horizontal axis, from our result, we know that the magnetic field varies linearly when we are inside the cylinder until we get to a value equal to mu naught I over 2 pi a. And remember, this is because we're enclosing more and more current. Therefore, the magnetic field is increasing in magnitude until we get to the surface. And then once we get to the surface, we're not enclosing any more current. So now we're just getting farther away from the current source, and then the magnetic field varies inversely with distance. So it varies linearly with distance until we're enclosing all of the current. Then it varies inversely with distance.